Okay, for problem 1, we are given two matrices A and B, and we are told to find C, where C is equal to the inverse of B times A. So the first step that we need to do is we need to calculate B inverse A. B, the inverse of matrix B. Okay, so to do this, we need to remember the formula for the inverse of a matrix. So if we have some matrix P, where we have A, B, C, D, the inverse of P equals 1 over the determinant of P, so determinant of P, times we switch the main diagonal here, and then we have negative B and negative C. So that's the general formula for the inverse of a matrix. Okay, so that means that the inverse of B will equal 1 over the determinant of B times 5, negative 1, negative 1, 0. And the determinant of B, we calculate that. So the determinant of a 2 by 2 matrix is the product of one diagonal, and then you subtract the product of the other diagonal. So in this case, that is 0 times 5 minus 1 times 1, which means that this is equal to 1 over negative 1 times 5, negative 1, negative 1, 0, which means the inverse of B is equal to negative 5, 1, 1, 0. Okay. So now the next step is we have to multiply the inverse of B times A. So we calculated the inverse of B to be negative 5, 1, 1, 0. A is equal to 1, 1, 3, 2. Okay, and the way we do matrix multiplication is to find the value of the entry in the first row and first column, we take the entry in the first row of the first matrix, and then the first column of the second matrix, and we take their dot product of the row and of the column. So in this case, that would be negative 5 times 1 plus 1 times 3. So we do the same thing for the other other 3 entries here. So the entry that goes in the first row, second column would be the dot product of the first row in our first matrix and the second column in the second matrix. So that would be negative 5 times 1 plus 1 times 2. The entry down here, that's the dot product of the second row times the first column. So this is the entry in the second row, first column. So that would be 1 times 1 plus 0 times 3. And for our last entry, we take the dot product of the second row, second column. That is 1 times 1 plus 0 times 2. Okay? And then now if we do all the math, we should get negative 2, negative 3, 1, 1. And so our final answer wants us to add up. So this is the value of C. C is equal to negative 2, negative 3, 1, 1. Our final answer, however, is the sum of all entries in the matrix. So negative 2 plus negative 3 plus 1 equals negative 3. So our answer is A. Okay, problem 2 says let A be an m by n matrix and let R be the reduced row echelon form of A. Which of the following statements must be true? Okay, so I think to understand this problem, it's good to have an example. So our example for some of these statements will be 1, 1, 2, 2. and we need to find the reduced row echelon form of this matrix. So the reduced row echelon form is a form of a matrix where so the first non-zero element in each row must be 1, and okay, I'll write this down here. So the first element, first non-zero in each row is 1, and so this element is called the pivot, the first non-zero element, the pivot, and the second rule is that each column has exactly one, not exactly, at most one pivot. So that's just what they mean by row reduced echelon form. And we can convert a matrix to its row reduced echelon form by interchanging the rows, by multiplying rows, or by subtracting / adding one row from another. So in this case, the way we get to the row reduced echelon form is we leave the first row the same, and then we subtract. So row 2 equals, we subtract 2 times row 1 from row 2, and we get 1, 1, 0, 0 as the row reduced row echelon form of A. And as you can see, this is our pivot, and there's exactly 1 pivot in this column and 0 pivots in this column. Okay, so now the question asks, which of the following statements must be true? Statement 1 says the null space of A is equal to the null space of R. So the null space of a matrix is, if we have AX, well actually, the null space of a matrix A is all solutions that satisfy this equation. So AX equals 0, equals a 0 vector. So it's all the set of all X that satisfies that equation. The way we calculate the null space of a matrix A is first we find the reduced row echelon form. So if we were to find the null space of this matrix here, we would convert it to the reduced row echelon form, and then we solve the augmented matrix for that reduced matrix. So in this case, we would solve this augmented matrix here to determine the null space of A. And the key here is to recognize that since R is already in the reduced row echelon form, we actually end up solving the same augmented matrix ultimately, meaning that the null space for A and the null space for R would be the same. So statement 1 is true. Okay. Alright, so statement 2 says the column space of A is equal to the column space of R. So the column space is the set of all vectors, the space of all vectors spanned by the columns of a matrix of A. So in this case, we repeat a similar process where we take the row reduced echelon form of A. So to find the column space of A, I would take the row reduced echelon form, and then I have to find all columns with a pivot. So in this case, the column with a pivot is the first column, and the corresponding column in A gives us the corresponding columns. So in this case, we only have one pivot, but if there were multiple pivots, it would be all of those corresponding columns. the corresponding columns in A gives us the column space. So in this case, the column space of A is 1, 2. Now, if I were to find the column space of R, we already put R in the row reduced echelon form. However, this time the corresponding column for the pivot is 1, 0. So in this case, we have a counterexample that shows us that the column space of A is not necessarily equal to the column space of R. So that's why 2 is false. And in general, this is an important concept to understand, that when you are finding the column space of a matrix, make sure that you're picking the columns from the original matrix and not from the reduced row echelon matrix. Okay. The third statement says rank A equals rank R. So rank is the number of linearly independent columns in a matrix. And the way we calculate rank is for any matrix, we first take the row reduced echelon form, and then we count the number of pivots. So in this case, we only have one pivot, and this statement is true because, similar to the null space, the rank is completely dependent on the reduced row echelon form of a matrix. So since R is already in its reduced row echelon form, it has the same number of pivots as A. So that would make 3 true as well. Okay, number 4, statement 4 says, if A has a pivot position in every column, then AX equals B is inconsistent for any B in Rm. AX equals B is consistent for any B in Rm. Okay, so recall that one definition of inconsistency is when we have an augmented matrix. So we can tell basically that a matrix is inconsistent if the final row of the matrix is as such, so 0, 0, 0, 0, 0, B, where B is not equal to 0. So if we have an augmented matrix like this, where the last row in the matrix is 0, and the final element in the solution is non-zero, then we have an inconsistent matrix. So using this information, we can come up with a pretty easy counterexample that shows that 4 is false. And the counterexample here is if A equals 1, 0, 0, 1, 0, 0, then B, we could have a B like 0, 0, 1. And this is an example of an inconsistent system, which shows that statement 4 is false. Okay, statement 5 says, if A is a square matrix and the determinant of R equals 0, then the determinant of A equals 0 as well. Okay, so to understand this last statement, we need to consider all the operations that we can do to reduce a matrix. So there are 3 operations that we use to reduce, to put a matrix into the reduced row echelon form. So the first operation is interchanging rows. And then the second operation is multiplying rows. So, yep. The third operation is adding rows together, adding rows together. I'll say that. You can add them together, subtract them together. Yeah. Okay, so for the first operation, so the nice thing about all 3 of these operations is that when we apply them to a matrix, we can also examine how each of these operations changes the determinant of the matrix. So if I interchange two rows in a matrix, the difference that occurs to the determinant is that we change the sign. So essentially we multiply by -1. When we multiply rows by a scalar, the determinant is also multiplied by that same scalar. So if I have a matrix like 1, 2, 3, 4, and I multiply the first row to become 2, 4, 3, 4, then my determinant of the new matrix would also be 2 times the determinant of the old matrix. And adding rows together results in no change. So what this means is that if we have a matrix A and the determinant of that matrix is 0, any change we do either doesn't change the value of the determinant, multiplies that determinant by a factor of some constant, or we multiply by -1. And if we start off with a determinant of 0, none of these changes, since they're all multiplication, none of these changes will change the determinant of the altered matrix. So that means that, yes, the determinant of R would also be 0. Because, like I said, multiplying by -1 or C, some constant C, has no impact on the determinant of 0. So that means statement 5 is true as well. And that means that our answer is A. Okay, problem 3 says, let L be a linear transformation from R3 to R3 whose standard matrix is this matrix, where A is a real number. Find all values of A such that L is not 1-to-1. Okay, so to understand this problem, we are going to want to use the invertible matrix theorem. So invertible matrix theorem. And the invertible matrix theorem consists of a lot of different statements that states that for an n by n matrix A is invertible. Invertible means that we can find an inverse if and only if, and there's a bunch of different statements. And so 2 of these statements are that the transformation, or we can just say, the transformation whose standard matrix is A is 1-to-1. So this is one statement in the invertible matrix, and the second statement is that the determinant of A is not equal to 0. Okay, so these are 2 statements in the invertible matrix theorem. And so the important line here is that it says A is invertible if and only if, and that, since we have 2 statements here, either both of these statements are true or both of these statements are false. So what this means essentially is that if I want to prove something like L is not 1-to-1, instead of working through how to show that relationship, I can find an equivalent statement, which would be that, in this case, the equivalent statement is determinant of A equals 0, and prove that instead. So using the invertible matrix theorem, I can simplify the problem I want to solve a little bit. So essentially, this means so by the invertible matrix theorem, L is not 1-to-1, is equivalent to determinant A equals 0. So now what I can do is I can, instead of solving, I can solve for all values of A that would make the determinant of this matrix 0. Okay. So for a 3x3 matrix, the way we find the determinant is we take one row, we can take a row or a column, and we have to expand and multiply. But in this case, there's a strategic way to picking the best row or best column. In this case, we want to pick the third column because, as you can see, there are 2 zeros here. And so now the formula would be 2 minus A times the determinant of A plus 1, A plus 2, A minus 1, minus 0 times this matrix plus 0 times this matrix. And one important fact here is that while we are multiplying out these cofactors, we need to consider the sign. So I like to think of it as a diagonal. It's like a diagonal grid. So in this case, 2 minus A, it's still positive. So we multiply 2 minus A times this sub-matrix over here. Okay, but choosing the third row to do this expansion makes our job a lot easier, because now I don't have to worry about this, and I don't have to worry about this either. So we have 2 minus A, and then the next step is to calculate the determinant of this 2x2 matrix. The determinant of a 2x2 matrix is a lot simpler. We take the first diagonal and then subtract the second diagonal from the first diagonal. So we have A times A minus 1 minus A plus 1 times A plus 2. And so that equals 2 minus A times A squared minus A squared minus 3A minus 2. And ultimately I get 2 minus A times negative 4A minus 2. Okay, and we want to find all values of A such that the determinant of this matrix equals 0. So if I set this equal to 0, the values of A that satisfy this equation are A equals 2 and A equals negative 1/2. So therefore our answer is C. Okay, this problem gives us 3 vectors, v1, v2, and v3, and then asks us which of the following statements is always true. Okay, first statement says v1, v2, and v3 are linearly dependent. Okay, so how do we show that 3 vectors, how do we determine whether they are independent or dependent? So the way we do this is we consider the matrix with columns that are each of these vectors. So in this case, that would be the matrix with columns v1, v2, v3. And then now we row reduce this to reduced row echelon form, and the number, if there are 3 pivots in the reduced form of this of this matrix, that means that all three of the vectors are linearly independent. So the number of pivots tell us how many of these vectors are linearly independent. So how do we row reduce? So there are three operations we can do. One operation is that we can switch rows. So I'm going to switch row 1 and row 3. That gives us 1, 1, 2, 4, 3, 7, 0, 3, 3, and 3, 2, 6. The next operation is we can multiply rows by constants. So I'm going to multiply row 2 by 1/4. I'm going to multiply row 3 by 1/3. And I'm going to multiply row 4 by 1/3 as well. Okay, so I get 1, 1, 2, 1, 3/4, 7/4, 0, 1, 1, and 1, 2/3, 2. Okay, next we can subtract and add rows together. So row 2 will now equal row 1 minus row 2. Row 4 will equal row 1 minus row 4 as well. Okay, and then I get 1, 1, 2, 0, 1/4, 1/4, 0, 1, 1, and 0, 1/3, 0. Yes. Okay. And then now I will do a few more. So actually, okay. So now I'm going to say row 4 equals 3 times row 4. I will subtract 1/4 of row 3 from the second row, and I will subtract the third row from the first row. So all of these operations will help us reduce this matrix. And you can see like I'm already almost there. So like the first step I did was getting rid of all of the other leading numbers in rows 2, 3, and 4. So I only have a 1 here. For a matrix to be in row reduced echelon form, the leading entry in each row must be a 1. This leading entry is called the pivot, and each column can only have one pivot, either one pivot or 0 pivots. So right now what I did here is I got rid of all of the other non-zero entries so that there's only one pivot in the first column. And now I'm going to like repeat so that there's only one pivot in the second column. Okay, so yeah, but after I do these operations, I get 1, 0, 1, 0, 0, 0, 0, 1, 1, and then 0, 1, 0. Okay, and then I will subtract row 4 from row 3, and then I end up with, and I will also subtract, we'll do that step later. Okay, so we get 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. And the last step here, I will subtract row 3 from row 1. And so I get 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0. And then now all I have to do is rearrange these rows. And once I rearrange the rows, I get the reduced row echelon form. And as you can see, I have 1, 2, 3 pivots. 3 pivots means that v1, v2, and v3 are linearly independent of each other. That makes statement A false. Okay. Statement B says v1, v2, and v3 span R4. This statement is false, and the reason is for any space Rn, if we have a set, so for any Rn, if V spans that space, then the size of V must be at least n. So for example, if I want to create a set that spans R3, I need to have at least 3 vectors in order to span R3. So in this case, to span R4, I need at least 4 vectors. 3 vectors, it's impossible to span R4. Okay, C says any vector in R4 can be written as a linear combination of v1, v2, and v3. So the definition of span is all possible linear combinations of a set of vectors, which means that statement B is essentially equivalent to statement C, which means that statement C is also false. Again, for the same reasons, it's not possible to span R4 without at least 4 vectors. Okay. D says, let A be the matrix whose column vectors are given by b1, b2, and b3. Then Ax equals b has a unique solution for any vector b in R4. Okay. So I think it's helpful to visualize. So they say A be the matrix whose column vectors are given by b1, v2, v3. That's essentially what we have over here. And if I have A, we can rewrite A as and let's say that x is equal to x1, x2, x3. So if I multiply A times x, I essentially get x1 v1 plus x2 v2 plus x3 v3, and x1, x2, and x3 are all scalars. So essentially, Ax is a linear combination of v1, v2, and v3. And we determined from statements B and C that it's not possible for a linear combination of these 3 vectors to span Rn, and that would also mean that it's not possible that there's a solution for any B. Because essentially, statement D is also equivalent to B and C. So that is also false. Because saying Ax equals B has a unique solution for any vector B in R4, that's equivalent to saying there's a linear combination. So for any B in R4, or any vector in R4, there's a linear combination of v1, v2, and v3 that is equal to that vector. Okay, and then statement E says, let A be the matrix whose column vectors are given by v1, v2, v3, then Ax equals 0 always has a unique solution. Okay, so we know that the way we determine whether Ax equals 0 has a unique solution is we need to row reduce A first, and if the row reduced echelon form has pivots in each column, that means that there's a unique solution. And And that's essentially what we did here. We started off with A. The row reduced echelon form is here, and as you can see from that, there's only one possible solution because there is a pivot in each column. So that makes statement E true. Another way you can think of it is that the null space, so the null space is the set of all vectors that satisfies this equation. So the null space is the zero vector in this case. So that's why E is true. Okay, this problem says let T be a transformation from Rn to Rm with standard matrix A. Which of the following statements must be true? Okay, so let's say we have A, and A is like a matrix. Let's move this. So this is A. A is a matrix, and since it's going from Rn to Rm, the dimension of this column vector would be n by 1, and this column vector would be m by 1. So suppose like this is A here, this is some vector like x, and this is b. You know, if we're doing a times x equals b, what is the dimension of A? Because the first statement here says A is an n by m matrix. So when we're multiplying two matrices together, the number of columns in the first matrix has to be equal to the number of rows in the second matrix, which means that in this case, the number of columns, the number of columns in A has to be n, and the number of rows has to be m. And this is just based on the multiplication rules for matrices. And so using that, we can determine that statement A is false. It's not possible to multiply an n by m matrix times a n by 1 column vector. Okay, and we know that this has to be n by 1 because the transformation is from Rn to Rm. So that's how we know n by 1 is here and m by 1 is on the other side. Okay, statement B says if T is 1 to 1, then Ax equals B has a unique solution for any B in Rm. Okay, so if T is 1 to 1, then Ax equals B has a unique solution for any B in Rm. Okay, so 1 to 1 means that for any B, for any, so if we have an equation Ax equals B, for any B, there is at most one x that satisfies this equation. So it's not possible to, if we have Ax1 equals B and Ax2 equals B, and we know that A is 1 to 1, or the transformation T with standard matrix A is 1 to 1, that implies that x1 equals x2. However, it does not say that there needs to be a unique solution for every B in Rm. That it doesn't say that, so that's how we know that B is false. And we can also think of a counterexample. So an example of a one counterexample could be the matrix 1, 0, 0, 1, 0, 0. So in this case, this would be a transformation from R2 to R3, and any this is 1 to 1 because it's not possible for us to have it's not possible for for us to have two vectors in R2 that map to the same vector in R3. However, there are plenty of vectors in R3 that don't have a corresponding solution in R2. So, like, for example, we could say this is A, and an example that, you know, as a counterexample could be like 0, 0, 1. Okay, so C is true, but we will come back to why it is true later. D says the columns of A are linearly independent if and only if rank A equals M. Okay, rank is the number of linearly independent columns in a matrix. And according to what we determined while we were determining if statement A was true or false, we said that the matrix A must have m rows and n columns. So rank is dependent on the number of linearly independent columns, meaning that and it's the rank is equal to the number of linearly independent columns. So if all the columns of A are linearly independent, they would equal n, not m. So that means D is false. Oops. D is false. We can also think of a counterexample for this one, like 1, 0, 0, 1, 0, 0. So, oh, this isn't a good counterexample. So actually, this would be a good counterexample. So in this case, the columns of A are linearly independent. 1, 0, 0, 0, 1, 0 are linearly independent. However, the rank of this matrix is equal to 2, not 3, like the statement claims. Okay, last statement, E. If the set V1, V2 through Vk spans Rn, then the set T of V1, T of V2, so on spans Rm. Okay, this statement is false. One way we can think about why this is false is consider a transformation that goes from a lower dimension to a higher dimension. So, for example, R2 to R3. The set 1, 0, 0, 1 spans R2. That's a basis for R2. The transformed set, the set T of V1, so transformation of 1, 0, the transformation of 0, 1, it's impossible for this to span R3. And the reason is, for a set of vectors to span some space Rn, we need at least n vectors. So to span R3, I need at least 3 vectors. Or like to span R4, I need at least 4 vectors. And in this scenario, we only have 2 vectors because in our initial set, we only had 2. So that's why E is also false. And if you want a more concrete example, we can say that the standard matrix for this transformation is 1, 0, 0, 0, 1, 0, which would make T of 1, 0 equal to 1, 0, 0, and T of 0, 1 equals 0, 1, 0. So we can see that this clearly does not span R3. Okay, last statement is C, which is obviously now we know it's true, but to see why this is true, there's 2 different strategies we can think of. So first, we want to consider what happens when m is less than n. So if m is less than n, we can show that essentially when m is less than n, it is impossible for t to be 1 to 1. That's essentially equivalent to saying that, yeah, if t is 1 to 1, then m has to be greater than or equal to n. So one way to understand why t can't be 1 to 1 when m is less than n is intuitively speaking, we're going from a larger dimension to a smaller dimension. So like if we're going from R3 to R2, there are more vectors in R3 that it's kind of impossible to map a one-to-one relationship onto R2. That's the intuitive way to think about it, but we can also think about it in a more factual way, which is that for a matrix, for T to be one-to-one, the columns of A are linearly independent. Because when the columns of A are linearly independent, that means that for any given vector, there's exactly one way to represent that vector as a sum of the columns. So if the columns are linearly dependent, that means there are multiple ways we could express some vector as a sum of the columns of A. Okay, but so yeah, we've shown that one-to-one implies that the columns of A are linearly independent. However, if M is greater than N, if M is less than N, meaning we have more columns here than we do rows, that means it's impossible to have independent column vectors. So that's how we know that statement C is true and is the correct answer. Okay, this problem gives us two vectors v1, v2. They say B is equal to the set v1, v2, where B is a basis for H. Which is a span of v1 and v2. They want us to determine if x is in H, and if it is, find the coordinate vector of x relative to v. Okay, so the coordinate vector, the coordinate vector is essentially if we have some linear combination of v1 and v2. It represents how we can, what kind of linear combination we would need to have x, to create x from v1 and v2. So essentially, if this is a linear combination of v1 and v2 that equals x, the coordinate vector would be c1, c2. Okay, so how we can do this, we consider a matrix with columns v1, v2, so 2, 1, 5, 3, negative 1, 4, and let u be the coordinate vector, and x, this all equals x. So the coordinate vector essentially just represents how can we represent x as a linear combination of v1 and v2. Okay, and now that we have this, all we need to do is solve for u. How we can do that is by creating an augmented matrix and calculating, now to find the value of u, we just need to row reduce this until we can determine c1 and c2. So I'm just going to write u equals this. Okay. So first step, I am going to divide the first row by 2 and divide the third row by 5. Okay, so then I got 1, 3 halves, 1 half, 1, negative 1, 3, 1, 4 fifths, 6 fifths. Okay, then we subtract. I'm going to subtract the first row from the second row, and the first row from the third row. And if I do that, I get 1, the first row stays the same, the second row becomes negative 5 halves, and the third row becomes negative 7 tenths. Okay, and then I can divide both row 2 by, well, I'll multiply by negative 2/5, and I'll multiply row 3 by negative 10/7. Okay. One, negative 1, 0, 1, negative 1. And row reducing will give us row reducing to the echelon form will give us a convenient way to find the solution for u. So C1 and C2. But in order to do that, we have to so first, now we have to we have a pivot here. We need to get a pivot in the second column as well. Okay, so how I'm going to do that is I'm going to subtract 2/3 or 3/2 of row 2 from row 1. So row 1 equals row 1 minus 3/2 of R2, and I'm going to subtract row 3. I'm going to subtract row 2 from row 3. Okay, so then I get 1, 0, 2, and 0, 1, negative 1, and then 0, 0, 0. So now this is in reduced row echelon form. We can tell because there is a leading, the first non-zero element in each row is a 1, and there's only that means this is our pivot. There's also only one pivot in each column, so there's 1 here and 1 here. And so that means that C1 is 2. So C1 is 2, and C2 is negative 1. So that means that, yes, since we found a solution, x is in H, and the coordinate vector is 2, negative 1. So our answer is B.
Okay, question 7 asks, which of the following collection of vectors is linearly independent? So let's think back to what linear independence is. Basically, if we have a collection of vectors, v1, v2 through vn, those vectors are linearly independent if, for the equations like c1 times v1 plus c2 times v2, so on, plus cn times vn is equal to 0. This equation has only one possible solution, where so basically any linear combination of that set of vectors can only equal 0 if all of the constants equal 0 as well. So C1, this C1, C2, Cn, those are constants. And we know a set of vectors is linearly independent if this equation has only one solution where all of the constants are 0. Okay, so first we can start by thinking of a few test cases where we know that a set has to be linearly dependent. So one example is when a set has the 0 vector. So cases where a set of vectors is linearly dependent. Okay. So 1 would be, okay, and the reason is fairly simple. If you have the 0 vector as a member of your set, there's going to be a million ways to have a linear combination of vectors where the sum of a linear combination of the vector set is equal to 0. And we can notice that option E has a 0 vector, so that means that E cannot be linearly independent. Okay, the second would be a case where one vector is a multiple of another. One vector is a multiple of another. So for example, if I had 1, 1 and the vector 1, 1 and the vector 2, 2 in a set, that would be a linearly dependent set because it's possible to have a combination of those two vectors, which would result in the 0 vector. And so if we look at C, like if we do a quick inspection, we'll notice that this vector and this vector are multiples of each other. If I multiply 2 times the first vector here, I get the second vector, which means that C is a linearly dependent set. Okay. The next would be if I have like for a n-dimensional vector, so like there are more than n vectors. So for example, if I have like a set of vectors which is 1, 0, 0, 1, and 1, 1, those vectors are in R2, they're two-dimensional, but I have 3 vectors in my set, I can immediately know that that set must be linearly dependent because it's impossible to have a linearly independent set in n dimensions that has more than n elements. So in this case, the set of vectors that violates this rule is B. So now you might look at B and think, wait, how does B violate that? B has 4 dimensions. Each of these vectors have 1, 2, 3, 4. It's 4-dimensional, and there's only 4 elements in this set. However, we can notice that the third value of each of these vectors is 0, which in some ways we can think of this as being, since the third value is 0 for each of these vectors, it's kind of like we only have 3 dimensions now, but 4 vectors in our set. And so since we have 3 dimensions, the greatest amount of linearly independent vectors we could have in that set would be 3. But we have 4, which means our set is linearly dependent. That's why B is not a solution either. Okay, so we have 2 left, and we can check. So the last way we can check, this is more of a method to checking if vectors are linearly independent. So we know, so the columns of a square matrix are independent if the determinant, so I'll just abbreviate it, determinant of the matrix is non-zero. So for options A and D, we can check if these 3 vectors are linearly independent or dependent by taking the determinant of the matrix that has these columns. So for option A, that matrix would be 1, 1, 0, 0, 1, 1, 2, 1, negative 1. And I can take the determinant of this. Okay, so we can do cofactor expansion now, and by the determinant formula, I get 1 times the determinant of 1, 1, 1, negative 1, minus 0 times 1, 0, 1, negative 1, plus 2 times 1, 1, 0, 1. Okay, then now if I solve, this first determinant would be negative 1 minus 1, which is equal to 2. Just keep that like that for now. Plus 2 times 1 minus 0. And I think that's equal to negative 2 plus 2, which equals 0. So since the determinant of this matrix is 0, that means that these three columns, the columns of that matrix, which are these three vectors, are dependent, which means A is not our answer either. So the collection of linearly independent vectors is option D.